In the previous video, we saw that n of A is given by the span of u, v, and w. And we mentioned that none of u, v, and w could be written as a linear combination of the other two. Now, what if we take a more abstract view? We just take the symbols u, v, and w and ignore what they are exactly, but retain their properties. That is, the properties of tuple addition and multiplying a tuple on the left by a constant are retained. So let me give an example of what I mean. So for example, if x is the linear combination given by u plus w, and y is the linear combination given by 3u minus 2w plus v, where minus 2w means plus minus 2 times w, then we can obtain 2x plus 1y as follows. So 2 times u plus w plus 1 times 3u minus 2w plus v, and we can carry these out. Remember that u, v, w are tuples, right? These tuples. But we don't really need to know all the entries to manipulate this. So this will be just 2u plus 2w plus 3u minus 2w plus v. And that will just give me 5u. And there's 0w plus 1v. And we can, of course, simplify this as simply 5u plus v. So with this understanding, we can form the following set S. So S is going to be the set of all linear combinations of u, v, and w. So I can form this set: alpha times u plus beta times v plus gamma times w, where alpha, beta, and gamma are real numbers. Of course, if you write out u, v, w explicitly as these tuples, S is simply the span of u, v, and w. But now I'm treating u, v, w as abstract symbol and form this set S. So each element is going to be called some alpha times u plus some beta times v plus some gamma times w. I would like to point out that each element of S is actually uniquely represented. We don't really need this in this video, but it's something that's worth mentioning. And the proof is going to rely on the fact that you cannot write u, v, w as a linear combination of the other two. So I'm going to skip the details here and move on to looking more deeply at the set S. Without knowing what u, v, and w are exactly, we can still see that S satisfies the following properties. So I have listed 8 properties here, some of which are obvious. So for example, right, if you take the last one, if you multiply S by the real number 1, well, if S is alpha times u plus beta times v plus gamma times w, multiplying this by 1, you just get back itself, so we get S. And some of these things, like the first and second property, are also easy to check. All you need to do is, for example, if you want to check the second property, you would take S to be alpha times u plus beta times v plus gamma times w, and S prime to be alpha prime times u plus beta prime times v plus gamma prime times w. And you just carry out the additions and compare the results. So most of these are not too difficult to check. The one property that is a bit unusual at this point probably is the third one here. There exists an element script O in S, such that S plus script O is S for all S in the set capital S. Now, what could this element possibly be? Well, if you think about it, it's just the element given by the linear combination 0 times u plus 0 times v plus 0 times w. Because if you add any other element in the form alpha u plus beta v plus gamma w, you simply get back alpha u plus beta v plus gamma w. So this is our element script O. The reason why I wrote down these 8 properties is not just because I know ahead of time that S is going to satisfy all these. Is that these properties define what is called a vector space. So you can actually talk about vector spaces in more general terms. All you need is a set. So in this case, I have the set S defined like this, but you can define S in any way you want. But you need the set S to have an addition that is defined on it. But you also need to define multiplication on the left of an element from S by an element from a field F. So what you need is a set S and a field F, and you need addition defined on S and multiplying S in S by, say, alpha in F on the left. That is, you need to make sense of this alpha times S. So this has to make sense. And the property is that if you take any S and S prime from S, S plus S prime, given by however the definition of addition is, must give you an element in this set S. And alpha times S, however it is defined, must also give you an element in capital S for any given element S in capital S and any field element alpha. So once you have these defined, you can check against these 8 properties. And if all these properties are satisfied, then what you have here is called a vector space. And as you can see, N of A is a vector space. So if I take S to be N of A and the field F to be R, clearly these properties here, which are called closures, are satisfied. And we have also seen that these 8 properties are also satisfied by this pair. So N of A is a vector space. And you can also check the following. This also gives a vector space, and normally we just write f of n if this is the understanding. So the scalars are understood to be from the field F, and each element is an n-tuple of entries from F. Now, the question that we are going to explore next is the following. If you are given a vector space, can you always express it as the span of a finite number of vectors, as we could for N of A? Right, for N of A, we could actually even compute a set of vectors whose span is N of A. Now to end, we'll just mention that N of A actually has a special name. It's called the null space of A. We'll see that given a matrix, there are other vector spaces that you can form from it.